Hello, my name is Jeff Wanko. I am a professor of mathematics education in the Department of Teacher Education. I'm also an associate provost here at Miami University. Today I want to talk to you about something involving mathematical puzzles. This is an area of interest of mine in terms of my own mathematical recreation, but it's also something I have studied in some of my own research. What I want to talk to you about today is the idea about a language-independent logic puzzle. Language independent means it's something where you don't need to know the language or the culture of the puzzle. You can still pick up the puzzle in no matter whatever country you're in, and you can work on solving it as long as you already know what the rules are. An example of a language independent logic puzzle is a Sudoku puzzle. Many of us have seen Sudoku puzzles in lots of different places. They are universal. You could pick up one in any different country and work on it, as long as you already know the rules. So another puzzle like this is what is known as a Shikaku puzzle, and that's what I want to talk to you about today. You should have a handout that comes along with this presentation. In the handout, you'll see some information about Shikaku. It's a puzzle that was designed and invented by a puzzle magazine from Japan called Nikolai. The Japanese translation for Shikaku has to do with the idea about divide by box or divide by squares. As you'll see in the example that I have here in the puzzle for you, in the packet, you'll see an example puzzle where on the left-hand side is the original puzzle, and on the right-hand side, you'll see the unique solution for that puzzle. What you'll see as you start to investigate this is you'll see that throughout the entire grid, it's been divided up into rectangles and squares, where each of those rectangles has a number inside of it, and that number represents the number of small squares inside that rectangle, or you could think of it as the area of that rectangle. So in mathematics, this is a great place for us to begin to talk to students a little bit about the dimensions of rectangles that could give you that number. So for example, if you see a number like the number 8, you could think about, well, what are the factor pairs that multiply to give you 8? And you can see in this example, I've got a rectangle that has dimensions of 2 by 4. 2 times 4 is one factor pair that can give you 8. But as you can see on the right hand side of the grid, there's a number 8, where in the solution, it actually is a 1 by 8. The only way that you could get this puzzle to work out is by drawing a 1 by 8 rectangle around that number 8. So my research has revolved around this idea about using these language-independent logic puzzles with students to help them to think about how they can develop their deductive reasoning skills. That is, what has to be true, what do I know has to be true, and why is that true? And then once I know that, what else do I know after that? This is the idea about a geometric proof that we see. It underpins all the work that we do in geometry and thinking about deductive reasoning. So what I want to show you here is how you can work through one of these puzzles in thinking about deductive reasoning once you know all these rules. And what you can see in these puzzles is the entire grid is divided up into rectangles or squares, where the number that's inside of that rectangle or square represents the area of that rectangle. You'll also see that none of these rectangles or squares in the grid overlap with other ones, and exactly one number appears in each of the rectangles when we're finally done with the puzzle. So in taking a look at that, keeping that in mind, those are the set of rules that we have. In taking a look at this, I wanted to show you that in your handout, we've got some other puzzles here, and I want to focus here on puzzle number 5. So I'm going to move over here to a document camera where we can talk through the solution for this puzzle as you would maybe work through it. Now, one of the great things is with each of these puzzles, every puzzle has a unique solution. There's only one way to draw a final solution for this puzzle, but there are multiple ways to get to that answer. So I thought I would walk through some of the different strategies you could use with a puzzle like this. Great place to start is to think about where is there a number that has only one way that you can draw a rectangle that's going to work for that number. Sometimes large numbers are great places to start. Other times you might want to look at corners. For example, a corner doesn't have as many different directions you can move out from. So when you look at the 6 in the top left-hand corner, and actually the 6 in the bottom right-hand corner as well with this puzzle, you'll see that there is exactly one way that you could draw a rectangle with an area of 6 that includes that 6 in the corner, and it does not have any other numbers included in it. So for example, if I were to draw a 1 by 6 for this 6, it would go too far and cross into some of these other numbers. But a 3 across and a 2 up rectangle gives you exactly an area of 6, and it does not overlap with any of the other numbers. Same thing works in the bottom right hand corner in this case as well. So if you draw that in, then you have to think about, what else do I know? Where else could I go in this puzzle that has exactly one way to do that? Now that this rectangle has been drawn, the 6 that's next to it has only one way that it could go. I can't go to the left from this 6, I can only go down and to the right. And the only way to get this so it doesn't intersect with any other numbers is, again, another 3 across, 2 up rectangle with an area of 6. Actually, the same thing is true for the one at the bottom. So this one's kind of great. It's working kind of across the grid with the same kind of idea. The only way I could draw a rectangle with an area of 6 now is to include the 6 in the corner and have it be another 3 by 2. Another place we could look is this 9 that's here. So the 9 is great because it has a 1 by 9 and 9 by 1 as possibilities. Either of those, though, are going to run into some of the other numbers and rectangles. However, don't forget that 9 can also be a perfect square. It's a 3 times 3, and that is going to fit in quite nicely here into our grid. Continuing down on the left-hand side, I could take a look at that number 8. So the 8 is kind of squeezed in there on the side. It's kind of hemmed in by this 12 that's here. The 8 can only be a 2 across and a 4 up, otherwise it'll run into some of the other numbers. Once that 8 has been drawn, right below it, there's a 2 that can only go over 2 and up 1. Now I finally get to see a 6 that's in a different kind of an arrangement. This 6, I can't go over 3 like I did with these other 6s, but I can go over 2 and up 3, taking me up to this point right here. Now my puzzle is filling in quite nicely. When I take a look at the number 12, it's here. It's a large number, so I've got lots of factor pairs for 12. A 1 by 12, 12 by 1, 2 by 6, 6 by 2, or a 3 by 4, or a 4 by 3. With my 12, since I can't do 12 over, by the way, you'll notice that this puzzle is in a 10 by 10 grid. I can't go over 12. Don't have enough squares for that. But I can go 2 and over 6. Once I do that, it's the only way that I could draw a rectangle. You might want to think through that to see if you can convince yourself of that, but it's the only way that rectangle is going to fit into this grid. Below that 12, I've got a 4 that can only fit in with a 1 by 4 and come all the way over to here because that's the only way that I can use up all of the squares that are in the grid. Now I want to think about this 4. This 4 is an interesting one because it could be a 1 by 4 stretching up 4 units, or it could be a 2 by 2 square. Either one is very possible right now. So another thing to think about with these puzzles is to think about every square gets used in the grid. So there has to be a number that stretches to cover every square. If I did draw a 1 by 4 box, for example, if that box were to be a 1 by 4 like that, this square down here cannot be reached by any other number by drawing a rectangle. So that tells me the only way that I can draw this 4 to work is to be a 2 by 2 square to fill in like this. Same way with thinking about this square right here. The only number that can reach that square is this 8. This 8 has to stretch down and fill in to take care of that region. Now the 2 is interesting. The 2 could go 2 across, 2 down. You'll see that if I did 2 across, it's going to leave me with another region here that can't get covered by another number. So this 2, we'll find out, has to be 2 down and 1 across. This 6 is another one of my 3 by 2 rectangles. Fills in quite nicely there. I'm left with a 3 and a 12. Once I take a look at that, the only way I could do that is to have a vertical 1 by 3 for the 3 and another rectangle with an area of 12, but this one being a 4 by 3. So here's an example of one Shikaku puzzle solution. What I've included in the packet are a number of other puzzles for you, a number of other 10 by 10 puzzles, including one of my favorites, puzzle number 6 with this string of 10s along this major diagonal. It's got 5 10s there. It'll be fun to try to figure out how to get those to fit in there. I've got some larger puzzles that are 18 by 10 puzzles, And once you get some larger grids like this, you can also include some larger numbers like this 18 that you'll see in here. And then finally on the last page, you'll see two 24 by 14 puzzles. And one of my favorites is this last one, puzzle number 11. It's got a great arrangement of starting squares, and it's really, really challenging to find where you can even start with this puzzle. I'll give you a hint, it's on the right-hand side of the puzzle. All right, so thank you for your time here with me today. I really appreciate you taking a look at Shikaku puzzles. If you have any questions, please feel free to reach out to me. I'm always happy to talk about puzzles. Have a great day.